Okay, so now that we've talked about an object, a single object that's being whirled about on a string that's providing a centripetal force that's keeping it in a circular path, or alternately a object whose tendency to go along a tangential path, according to Newton's first law, is being countered by a friction force that prevents sliding in that direction. So for instance, in that case, a car going around a corner. Now let's think about a rotating object. A rotating object is, well, an object that is rotating, like, say, that, which is now rotating about a particular axis. Where the stuffed bat is, I have no idea. One of my kids, I think, took it. Anyways, so a rotating object is something that is rotating about or spinning about an axis that is central to the object itself, although the object itself might not have matter at that central axis. You can think about that rotating object. Here it is. It was vaguely square, I guess. It was rotating about a center axis that's coming out of the page like this. It was a measuring tape. So as it's rotating, let me pick the word side so that you can see. As it's rotating around that axis, you can actually model every point on it, for instance, say that pink one I've just drawn, as a mass that is being rotated about on a string. So every point on this object can be seen as something going around the center axis like that. It's just that that larger object, the measuring tape for instance, is a collection of those points that happen to be attached to each other. Now that centripetal force that prevents, say, I don't know, this point on the object from flying outward, well, it wouldn't fly outward now, would it? Continuing in a straight line when I rotate this measuring tape, the force that prevents this from continuing in its straight line trajectory is now a set of molecular forces or intermolecular forces that hold this object together as a whole solid object. There are a couple of things we need to kind of get through before we fully are able to talk about rotating objects. We've already seen with objects going around a circular path. Whoops, that was a terrible circle. Here's the object, it wants to do that. Here's the centripetal force pulling it in towards the center. We can talk about its linear velocity. Its linear velocity is the circumferential distance, so the distance around the circumference of the circle that it travels per unit time. We can also talk about the angular velocity. So linear velocity, by the way, is symbolized V. Angular velocity, which is symbolized with a lowercase omega, is the number of degrees or more strictly speaking, radians that an object traverses, or a point on the object traverses, per unit time. There are 2 pi radians per circle. So for those of you who vaguely remember radians from some class in high school and prefer to forget it, I myself prefer to think about life in terms of degrees because that's how we talk in normal society. So angular velocity is either in degrees per second or more strictly, more formally, radians per second. There are good reasons for using radians. But none of them really apply to the sorts of problems we're going to do in this class. I want to think about one of the implications of linear velocity and angular velocity and kind of distinguishing the two. So picture the Earth. At the equator, the the circumference is around 40,000 kilometers. And we, of course, traverse that 40,000 kilometers in 24 hours, one time around, one day, which, if you kind of go through all of the arithmetic, you find is around 460 meters per second. Schlep north to Scotland, and you can find a place in northern Scotland where now the circle that somebody standing there traverses is only now 20,000 kilometers. So you've got the Earth, it's got its equator, it's rotating around its axis like so. This is 40,000 kilometers. And up here somewhere in Scotland, if you took a slice, that circle is only 20,000 kilometers. But our man in Scotland, his day is still 24 hours long. So he happens to be traversing 20,000 kilometers in 24 hours. He's moving more slowly than our folks down at the equator. Now the Scottish fellow is only going 230 kilometers per second. In both cases, they're traversing 360 degrees, one full revolution in 24 hours. They both have an angular velocity of 0.000174 degrees per second, but their linear velocities are very different. Well, who cares? Texas cares. For those who are not familiar with politics, perhaps you think that all the interesting politics is happening over here in Iowa, or did last night. In fact, we've decided that Texas is going to attack South Dakota. Dallas is approximately due south of Sioux Falls. Why they're attacking South Dakota, I don't know. You'd think they'd be allied. I'm going to now kind of make up some numbers for clarity and draw this seriously, not to scale. The numbers I'm writing here, please ignore the numbers themselves. Think about this from a conceptual point of view instead. Here's my missile here on the ground in its silo. I guess silos tend to be under the ground, but attached to the ground in Texas. Texas is not that far north of the equator. And so at this point in Texas, the ground and everything attached to it is zipping along at the right old velocity of, again, I'm kind of making up these numbers as sort of reasonable approximates. So let's say it's 400 meters per second. The ground is traveling that way at 400 meters per second. The missile in its silo, as long as it's attached to the ground, is traveling that way at 400 meters per second. Now let's see if I can draw a line freehand. I'm betting I can't. I'm going to pick a zone north of there. I want to think about that zone going through Oklahoma. It's significantly north of there. We just saw from the Scotland example that as you move to the north, your linear velocity, the velocity of an object on the ground at that more northerly point, is traveling more slowly than the linear velocity of an object at the equator. Let's say maybe 380 meters per second. Continue further north. Perhaps this slice is 360 meters per second. Once again, I'm making up these numbers. We know that we have to get to 230 up in northern Scotland, but this is seriously out of scale for the United States. I'm just taking big chunks to kind of make it a little more clear what's happening. All right, so when our missile, headed for South Dakota, launches from the ground in Texas, at the instant it comes out of contact with the ground, there is no longer a frictional force keeping it going along with the ground. That said, it has inertia. It has an inertia that keeps it moving eastward at 400 meters per second. There are no forces on it really other than gravity and air resistance, which we're going to just, air resistance anyways, we're going to ignore for now. So just keep in mind that at the instant it launches, and for all of its travel afterwards, it still has an eastward velocity of 400 meters per second. If it were to launch straight up and then fall straight back down, it would fall exactly in place, because while it's moving eastward at 400 meters per second, the ground right below it is also moving eastward at 400 meters per second. And so it would fall right back into its hole, assuming nothing bumped it. I think from that you can see where I'm going, because now instead of just launching it straight up, I'm going to launch it north. When I launch it north, then the missile is continuing to move eastward at 400 meters per second. Here I am over Oklahoma. The ground in Oklahoma is moving only 380 meters per second, which means that the missile has moved eastward faster than this point in Oklahoma has. The point it should be over is not the point it's in fact over. Our missile continues moving northward, but it also has an eastward inertial velocity of 400 meters per second. So when it gets up to this zone, the ground underneath it is moving at only 360 meters per second, and the missile, instead of being over this point where it should be, is over that point. Get up to the area of Sioux Falls, and suddenly, oh my God, we've bombed Wisconsin. We've started an all-out cheese war. The missile appears to have had a force that moved it east of north. This is yet another pseudo-force. We call that force the Coriolis force. And I guess this is kind of an indication of how times have changed, when I learned Coriolis forces in college, all of the examples in the textbook had the United States managing to do the calculations to get an ICBM to land somewhere in Russia. The Soviet Union, then Soviet Union, now I guess former Soviet Union. But we have somewhat more peaceful ways of thinking about the Coriolis force, although no less tragic. I've put at the bottom of this slide a clip of Hurricane Katrina. Cue it up at 42 seconds and keep a watch of it there. The main thing I want you to observe, and really if you've ever seen a weather satellite image of a hurricane or similar storm, you don't actually need to look at the clip. You've seen it. What you notice is that the clouds end up rotating in a direction like this. That rotation can be quite fast, and is what causes the significantly fast and damaging winds that we experience when we have a hurricane. All right, so let's see what's happening here. Here you are, north of the equator. I'm going to put the equator down here. Florida's up here somewhere. Caribbean islands. A low pressure area of air happens. I'm not going to get into meteorology. You can do that in another class, or think back to probably elementary, middle school science. But a low pressure area appears. The surrounding high pressure gases, of course, want to move towards the low pressure area. Let's examine a packet of high pressure gas here. It attempts to move that way. But as it moves that way, just like our missile launched from Texas, it ends up diverting off this way due to the Coriolis force. It's attempting to move northward. The high pressure gas had a certain eastward velocity here, nearer to the equator. It's moving to an area where the standard eastward velocity is much less, and therefore it kind of moves that direction but misses. Make the same argument for our high pressure area that starts north of our low pressure area. It wants to move straight down. It ends up diverting off. High pressure areas to the exact east and west are not diverted at all, because the velocity of gas at this point is equal to the velocity of gas at these other points. They're all in that same north-south zone relative to the equator, so there is no change in the linear velocity that goes along with the sort of slice of the Earth that it's associated with. Hopefully you can see that this process, as long as you have a low pressure area being maintained here and high pressure gases around it, this process will cause a continuous flow and continuous sustaining of the low pressure area as the gases that are attempting to fill it find that they cannot actually get there. They keep missing. So you get the buildup of a very rapid rotational system. And now you know where we get hurricanes. It's due to the Coriolis force.